In this video, we are going to take a look at static equilibrium, this time with force and torque. So last semester we just looked at it in terms of force. Now we're going to redefine static equilibrium as when the net force and the net torque acting on the object are zero and the object is stationary. So the goal with these problems is we have to get the force and the torque to balance. So here's our first problem. We've got Bob standing on a bridge. The bridge itself weighs 10,000 newtons. The span between supports A and B is 80 meters. Bob, whose mass is 100 kilograms, stands 20 meters from the center of the bridge as shown. Find the force exerted on the bridge at position A and position B. So since we know we want to get the forces and the torques to balance, let's start by drawing in some forces on this diagram. So we've got the force from A, which I'm going to call FA. We've got the force from Bob, which I'll call FBob. And we also know that Bob is 20 meters from the center of the bridge. So the center of the bridge is 40 meters. So Bob is this 20 meters. And we know that the entire bridge is 80 meters. So we've got the force from Bob. And then we've got the force from the bridge itself, which I'm going to draw right in the center, which is right around here. So I'm going to call that F bridge. And then we've got the force from the support at B. So we know that the forces have to balance. What that means here is that all of the forces pointing up have to balance out with all of the forces pointing down. So we want to say FA plus FB equals FBob plus FBridge. And we know that the bridge has a weight of 10,000 newtons, so it's going to be pulling down with 10,000 newtons. And Bob has a mass of 100 kilograms, so his weight is going to be 100 times 9.8, which is 980 newtons. So he's going to be pushing down on the bridge with 980 newtons. So we can start filling in some numbers here. So we know that FA and FB have to add up together to 1,000 or 10,980 newtons. However, we still have to look at the torques going on here. So I'm going to reimagine that this support at A is actually a hinge. So imagine that the bridge could actually, and here's Bob, could actually rotate around that hinge. We don't want a bridge to be able to do that. So that's why we need to make sure that the torques balance. So if we're thinking about torque, we don't actually have to worry about the force from the support at A, because remember that the torque is equal to FD, and if D is 0, then it's not going to cause a torque. So we don't have to worry about FA. We do have to worry about the force that Bob is putting on the bridge, the force that the bridge is putting on itself due to its own weight, and the force that B is putting on the bridge. So first, we know that Bob is going to cause a clockwise torque, and he's going to exert a torque that we'll call tau Bob, and the bridge, which is that way, is also going to exert a clockwise torque, and we'll call that tal bridge. And then the support from B is also going to exert a torque, but that torque is counterclockwise. So for this bridge to be in static equilibrium, in other words, in order for it to not rotate, we need the clockwise torques to add up and equal the counterclockwise torque. So we need tau bob plus tau bridge to equal, we'll call that tau b. Lots of b's here, so I'm writing out these full names so that we don't get confused. Okay, so what would the torque from Bob be equal to? Well, the torque from Bob is going to be the force he's exerting, which is 980, times his distance from the axis of rotation, which is 20 meters. And we can figure that out because it's just 40 minus 20. He's 20 meters from point A. So let's substitute that in there, 980 times 20. And what is the torque from the bridge? Well, we're going to pretend that since this bridge is uniform, that all of its mass is concentrated in its center of mass. So at 40 meters from the axis of rotation. So the torque from the bridge is going to be the force of the bridge, and there's the 20 there, times its distance from the axis of rotation. So that's going to be 10,000 times 40. And then what is the torque from B going to be? Well, it's going to be the force of B, which we don't know yet, times its distance from the axis of rotation. And we know that the bridge is 80 meters long, so that's going to be 80. So we're going to say 80 FB. So we can now see that we can use the expression for torque to find FB, plug that back into our equation for forces to find FA. So let's just go ahead and do a little bit of arithmetic and algebra here. So when you add all of that up together, you get that. And then you can solve that for FB and get 5,245 newtons. Then you can go ahead and plug that back in right there. So FA will end up being 10,980 minus 5,245. And you get that it is equal to 5,735 newtons. And I want to point out that it totally makes sense that FA is bigger than FB. Since Bob is standing closer to this end of the bridge, FA would have to provide more support than FB. And that's how you solve problem number 1 here. And here's problem number 2. So we have a uniform beam, that's this thing here, 2.2 meters long with a mass of m equals 25 kilograms, is mounted by a small hinge on a wall as shown. The beam is held in a horizontal position by a cable that makes an angle of theta equals 30 degrees. The beam supports a sign of mass 28 kilograms suspended from its end. Determine the components of the force that the smooth hinge exerts on the beam and the tension in the supporting cable. So first, let's just label some stuff on this diagram. And that's 28 kilograms. And then this is 25 kilograms. And this whole length is 2.2 meters. Okay, so again with this problem, we know that we need the torques and the forces to balance. So let's draw in some forces here. So first, let's draw in the forces from the hinge. So the hinge is going to exert a horizontal force on the beam, and I'm going to call that FHX. And then it'll also exert a vertical component on the beam, which I'm going to call FHY. Then we've got the beam itself. The beam has a mass of 25 kilograms. And we want to multiply that by 9.8 to get its weight. So the force that the beam is putting on itself is equal to 245 newtons. And then we've got the sine. So the sine is 28 kilograms. Multiply that by 9.8. So the force from the sine is equal to 274.4 newtons. And then we've got the tension from the cable. I'm going to call that T. And we know that there will be a y component, which I'll call Ty, and an x component, which I'll call Tx. So we need to look at three different things here, essentially. We need to look at the forces in the x direction, we need to look at the forces in the y direction, and we need to look at the torque. So I like to make a little chart so I can organize all of my information. So for my x forces, well, the only forces I have in the x direction are the force from the hinge in the x direction and the tension in the x direction. And those are in opposite directions, so I know they have to equal each other. So I'm going to say FHX equals Tx. And I can break this tension up into components. So I know that Tx is going to equal T times the cosine of that angle. So those are my forces in the x direction. Now I'm going to have my forces in the y direction. So I have more things going on there. So like with the problem with the bridge, I want all of my forces going up to equal all of my forces going down. So my two forces going up are the y from the hinge and the y from the tension. So I'm going to have FHY plus TY. And my forces going down are the force from the beam itself, and then the force from the sine, which is just the weight of the sine and the weight of the beam. So that's going to equal 245 plus 274.4. So FHY plus TY is going to equal 519.4 newtons. Then I want to consider my torque. So my hinge is my axis of rotation. So again, similar to the bridge problem, I don't have to worry about the torque from the force from the hinge because that's at a distance of 0 from the axis of rotation. So I only have to worry about the forces from the beam itself, the force from the sine, and the force from the tension. Also remember that if there's an angle involved, the torque is equal to FD sine theta. So I'm going to change my color real quick. We know that the force from the beam is going to cause counterclockwise torque. And the force from the sine is also going to cause a counterclockwise torque. And then the force from the tension is going to cause a clockwise torque. So we want the counterclockwise torques to equal the clockwise torques. So we're going to have the torque from the beam plus the torque from the sine equaling the torque from the tension. Okay, so the torque from the beam is going to equal its force times its distance from the axis of rotation. Like with the bridge, we're going to pretend all of the mass of the beam is concentrated at its center of mass, which is 2.2 divided by 2, so that's at 1.1. So we're going to say that it is 245 times 1.1. And then the torque from the sine is its force times its distance from the axis of rotation, which is 274.4 times 2.2. And since there's an angle involved here, the torque from the tension is going to equal its force times its distance from the axis of rotation times the sine of the angle it's being exerted at. So we don't know the force, so we're going to leave that as our variable t. D is 2.2, and then the sine of 30 degrees. So now we just have to solve this expression for t, and we can easily use that to figure out our other information. So if we do 245 times 1.1 plus 274.4 times 2.2, we get 873.18, and that'll equal 1.1 t. Then we solve for t, and we get 793.8 newtons. So we've found the tension in the cable. And we can plug it into our y, because we can simplify this here to t sine 30. That's just the y component of the tension. So we're going to have FHY plus 793.8 times the sine of 30 equals 519.4. And then we can calculate that the y component from the hinge is equal to 122.5 newtons. Then we can also plug the tension we found into our expression in the x direction. So FHX is going to equal 793.8 times the cosine of 30, which ends up being 687.5 newtons. So notice that the tension in the cable had to be pretty high because it had to balance out not only with all of the forces, but with the possible rotation caused by those forces. All right, one last problem. We have a uniform steel beam that has a mass of 940 kilograms. On it is resting half of an identical beam as shown. What is the vertical support at each end? So this is going to be 940 kilograms. So that's 940 kilograms. So the mass from that, or the weight from that first beam is going to be 940 times 9.8, which is 9,212 newtons. And then 940 divided by 2 is 470 kilograms. And then that weight is going to be 470 times 9.8, which is equal to 4,606 newtons. We need to make sure that the forces and the torques balance. So we're going to have the force from this end, which I'm going to call F left, and I'll call this one F right. And then we've got the two beams, which I've already drawn in. So like with the other problems, we want the forces going up to equal the forces going down. Otherwise, it would go up or down, which we don't want to happen. So we want to say that F left plus F right equals 9,212 plus 4,606. And that ends up being 13,818. Okay, now let's look at the torques. So we're going to make this left end our hinge. So we don't want rotation around that hinge. So the torques causing clockwise rotation have to equal the torques causing counterclockwise rotation. It's really similar to the other ones we've looked at. This beam would be causing clockwise rotation, and that would be clockwise. And then this would be counterclockwise. And I just realized that up here I mislabeled. Oh, yeah, I mislabeled these as, that should actually be clockwise and clockwise. And then that one is counterclockwise. So the torque from the little beam plus the torque from the bigger beam has to equal the torque from the support on the right. So it's going to be torque from the small plus the torque from the larger one equals the torque from the one at the right. So notice that we're not given the length here, but we do know that this beam is going across the whole thing, and this one is just going across half of it. So for this one, we want to say that all of its mass is concentrated in its center of mass, which would be L over 2. And then this one is going to be concentrated in its center of mass, which would be L over 4. So L over 4, L over 2, and L are going to be our distances from the axis of rotation. So we are going to say that the torque from the smaller one is its force, which is 4,606, times its distance from the axis of rotation, which is L over 4, and then the larger one, 9,212, times its distance from the axis of rotation, which is L over 2, and then the force from the right one, and that's just times L. So now notice that all of the L's cancel. We can divide both sides by L. So we want to make sure we're doing all of our algebra correctly. So 4,606 divided by 4. And 9,212 divided by 2. And this looks like the word fright, but I hope you guys aren't too frightened by this. You just have to make sure all of the forces and torques balance. So when you add those together, you'll get that the force on the right is equal to 5,757.5 newtons. Then you can go ahead and plug that in right there and get that the left-hand force is equal to 8,060.5 newtons. So hopefully you have a better idea of how to solve static equilibrium problems.